All right. 1.3, we've got rate of change and behavior of graphs. So the average rate of change, sometimes we write as the AROC. I used to write ARC, but people got it confused with some trig stuff. So AROC is kind of a fancy word for your slope. If you remember your formula for slope is y2, not minus itself, that would always be 0, wouldn't it? Y2 minus y1, in other words, the change in your y value, divided by the change in your x value. And sometimes we note that as delta y over delta x. So when asked to find the average rate of change of something, know that you need 2 points, 2 data values in order to determine that. Also remember, when you're finding the slope, it really, in the long run, it really doesn't matter which point you start with, as long as you start from the same point. You start with a point from the year 2000, the y value from the year 2000, the x value from the year 2000. Just be consistent. Now, when you are asked to interpret an average rate of change or a slope, and by the way, here's a little foreshadowing. Most of you are taking pre-calc because you plan on taking calc, right? You plan on taking calculus. That's your whole goal. Calculus is just the study of slope. That's all it is. So really get the interpretation down for your average rates of change. You don't have to write this, but instead of just always looking at a line, most functions are fluctuating. So the derivative is just that instantaneous slope at one particular point. Like if you were to take a tangent line just at that curve, that is your derivative, is the slope of that line. So don't freak out about calculus being such a scary word. It's really not. It's just slope. That's all it is. It's a study of slope. Okay. So when interpreting the ARC, there are 5 things that you need to mention. First of all is the when. In other words, what is the time frame? For example, and I'll put time in quotes here. If your 2 points, they say, you know, how much has your salary changed, or what's your average rate of change in salary between 1950 and you know, 2010, the average salary. You would have to state in your interpretation what time frame you're looking at. Between the 1950s and 2010, the average rate of change in salary was, you know, increased by this much per month or this much per year. Also, the output of your Y units. In other words, what are we studying? So again, in my example of salaries, the time frame was between 1950 and 2010, but I was studying the average salary or average income. So the average income, which is what we're focusing on. The third thing is whether or not it's increasing or decreasing, okay? If it's a positive slope, then it's increasing. And if it's a negative slope, that means it's decreasing. You also want to say the word average, because again, looking at this picture here, things can fluctuate. You know, blood pressure can go up and down, but you are looking at the overall average from one point to the next. So you need the word average because it doesn't mean that every equation is linear and there's a constant change. So average is good. And then the fifth thing is be sure that you give us the average rate of change, the actual slope value with its units. Output units per input units. So think of it like this, you know, you have the change in Y value over the change in X value. So if the Y value is dollars, oops, I'm gonna put $sign, but if the X value is in dollars and the Y value is in dollars and the X value is in years, then that equals dollars per year. Okay, so let's actually do one, kind of put it all together. I'll leave those up so we can see them though. So we got table 1 lists the average cost in dollars of a gallon of gasoline for the years between 2005 and 2012. Now it didn't look like it increased consistently. Between 2005 and 2006, it increased by 31 cents, but between here and here, it increased by 22 cents. So it's not a linear function. So we're not going to have a consistent slope. So that's why it's asking us to find and interpret, okay, the average rate of change. Okay, so again, that's your hint that they're asking us for the slope between 2007 and 2009. So that means we're looking at 2007 and 2009. Let me blow those up a little bit. So remember, to find our slope, we have to have 2 points. So which is our input value? It's weird because they have Y and C of Y. It's like, wait a minute, there's no X, there's a Y and a C, so which is which? So it is Y. Normally, we think of Y as the output, right? Y is always our output, but they're tricking us here. They're using Y as our input value. So always think of it in terms of either the notation. If they're using the function notation, that is always our output. But also in context of the problem, years will never be dependent upon something else. It's going to be 2007, and then it's going to be 2008. The year's not going to change due to gasoline prices. The gasoline price may change based on the year. So we have the year 2007 with 2.84 as the price of gas. And then we have a second point of 2009 with the price of gas 2.41. Remember, your Y is what you're actually studying. We're not studying the years, we're studying the price. So that always goes on top. So we can do 2.41 minus 2.84 divided by 2009 minus 2007. And let's see, what do we get? We get approximately a negative 0.215. Remember, when you're finding your slope, the top number was the price in dollars, and the bottom was in years. Try to keep those 5 things in sight there when we interpret what we found. So we want to say between 2007 and 2009, okay, the average price or cost for a gallon of gas or gasoline. Okay, so there's the second thing. What was our output? What are we studying? Decreased. Okay, so that was real quick, right? Oops, that was number 3 already. One word, decreased. And average, there's number 4. Because again, it fluctuated. It looked like it went up between 2007 2008, but then it plummeted down in 2009. So that's why we have to say an average of, and what did we find? It was a negative 0.215. So that is $0.215 or 21.5 cents. Okay. When it comes to money, both of them are fine. Both of them are fine. You could leave it in dollars or you can change it into cents. If it is a currency you're not familiar with, please just keep it in the decimal form with whatever units they gave you, okay? So we can keep the dollars. We can keep the dollars, and we can say it decreased an average of 0.215 dollars per, we'll just even write it out right now, dollars per year. Now, if you want to put $0.215 per year, I would accept that as well, because you do have the units of the dollar, you do have the per year.
The next example reads, near the moon, the distance an object falls is a function of time. It is given by the function d of t equals 2.667 t squared, where t is in seconds and d of t is in feet. If an object is dropped from a certain height, find the average velocity of the object from t equals 1 to t equals 2.
When you were finding the average velocity, we were going, wait, they didn't ask for slope, they didn't ask for a rate of change, but velocity is a change in distance per time, okay? So yeah, so when you read it, you go, oh my gosh, this feels like a physics problem, and the wording might throw you off. So sometimes you have to kind of read between the lines to go, okay, what is velocity? What are some examples? Oh wait, that is a ratio. That is a slope that I'm looking for. Cool.
So recall, in order to find the slope, we have to have 2 points. We know our first t value is 1, so if we plug it into d of t, we would get an output value of 2.6667. And if we plug in 2 into d of t, then we get approximately, let's see, 10.6668. So now we need to find the slope, and remember, when we do that, we subtract the y values, what it is that we're studying. So we get 10.6668 minus 2.6667. And then we also have to subtract the t values, our input values in the denominator, which would be 2 minus 1, to give us a slope or an average velocity of 8.0001.
Now remember, the top number was your distance. Is that correct? So the top number was in feet. Your bottom number was in seconds. So when we interpret this, we want to be sure that we give it in terms of feet per second. And remember, we have to have our 5 things. So what is our time frame between, here, between, we'll say between seconds 1 and 2. One and 2. What is it that we're studying? Average velocity, okay? So the average velocity, how do we know it increased? Yeah, because it was a positive number. So the average velocity increased an average of 8 feet per second. Oh, wait. Sorry. This is the average velocity. The average velocity is 8 feet per second. It was the average distance that increased an average of 8 feet per second. So it's the distance, which is what we're studying, but we found the average velocity. So if we're looking at the average rate of change, we can interpret it that. Otherwise, we can just say the average velocity between seconds 1 and 2 is 8 feet per second. So on this one, it's a little bit different. We're finding the average rate of change of this function, but notice the interval isn't just, 5 and 7. We are using an expression as one of those endpoints. So we have to be careful about our algebra and simplifying stuff when working these, but the formula is still the same. So we still need 2 points. In other words, the slope, we're going to need the function value at 5 plus h, whatever that looks like, minus the function value at 5. So there's y2 and y1 divided by, this is 5 minus 5 plus h, the x values. 5 plus h minus the 5. So y plus y2 minus y1 on top, and then the x values on the bottom. So let's focus on finding that y sub 2, right? This is like y sub 2 minus y sub 1. This is x sub 2 minus x sub 1. Because we're given the function, the x squared plus 2x minus 8, we can actually plug in the 5 and the 5 plus h to actually find those values. We'll find y sub 2, which is f of 5 plus h. And what that means is we're going to take this function here, the x squared plus 2x minus 8, and instead of the x that's being squared, make this a little bit bigger, instead of the x that's being squared and 2 times the x minus 8, we're going to plug in 5 plus h for every x. So we have 5 plus h here. We have 5 plus h there. So we can simplify this if we expand the 5 plus h squared. So just this first part here, we would get 25 plus 10h plus h squared. Okay, if you're not sure where that's coming from, try purple. That's 5 plus h times 5 plus h. If you were to FOIL, right, we would get 25 plus 5h plus 5h plus h squared. Okay, so that's that first part there. Then we distribute the 2. We get 10 plus 2h and the minus 8. And then let's clean it up, right? It's a quadratic. Let's put it in proper format. We get h squared plus 12h. Let's see, 10 minus 8 is 2, so we get plus 27. So this entire trinomial there represents our y value at 5 plus h. So let's take a look at y sub 1. That's the easier one. F of 5, we just get to plug 5 in for everything. So we get 5 squared plus 2 times 5 minus 8. Minus 8, and that just gives us a 27. So we have an expression for the y sub 2, the part up here in the top, the f of 5 plus h. And we have an actual numerical value for y sub 1, the f of 5. So we can actually plug those in. 8 squared plus 12h, and again, I'm finding the slope here. H squared plus 12h plus 27, that's my y sub 2, minus my y sub 1, which is 27. And then we have to put in our x values. So our x values at f plus h is in fact 5 plus h, 5 plus h, minus our first x value, which is 5. So at the top, we have x squared plus 12h plus 27 minus 27. And at the bottom, 5 plus h minus 5. We combine our like terms there. That gives us an h squared plus 12h over h. So that gives us an h plus 12. Just remember, whenever they give you an interval, like they did here, those two values are your x1 and x2. So in order to find your f1, f2, you have to plug those values into the function. We've got increasing and decreasing intervals of a function. So when they say that a function is increasing, that means the average rate of change or the slope is positive. So the graph is going up left to right. Okay. Doesn't mean it's a straight line. It can go up curving like this. It can go up curving like that. But it's just increasing. And we always read it left to right, like an English sentence. A function is said to be decreasing when the average rate of change or slope is negative. So again, that just means it's going down left to right. Could be curved, just going in the downward direction. When you are asked to find the intervals or to give the intervals of either increase or decrease, this is where some people get confused. It is always written in terms of the input values. In other words, what is normally the x value, and we use parentheses. If you use a bracket, that means it's included, and it's hard to be still increasing at the end point, right? Because there's some points where it's not increasing or decreasing, it's just flat. So let's take a look at this guy, for example. So we want to determine the intervals of increase and decrease. So we're going to use interval notation. If there's more than one interval, we're going to use the union symbol. Everything's going to be in parentheses, and we're only dealing with the x's. Because remember, in order to be a function, the x's don't repeat. The y's can repeat, but the x's don't, so we have to use the x's. So let's take a look at this first part of the graph here. Is it increasing or decreasing there on the left? It's decreasing, good, it's going down. And then it kind of changes direction here at 1. So we can write that as our first interval of decrease from -infinity all the way down to 1, parentheses. And sometimes it's helpful to even mark all of your, we'll give them names here in a minute, but the vertexes, the turning points, we're going to call them local max and mins. But these are kind of all the points here where it's neither increasing or decreasing. It's like max and mins. So let's look at this middle guy here. Between those 2 points, they're in yellow.
Notice that it is increasing left to right between 1 and 3.
So notice I'm not using the y value of 1. I'm talking about, you know, these x's here and these x's here. Because if we look at the y value of 1, don't write this down, but if you look at the y value of 1, it's included here, it's included here, it's included here. We wouldn't know which interval you're talking about. We never want to use the y values when talking about intervals of increase and decrease. Let's take a look at this tiny little interval right here. Decreasing, good. So we're going to do union, and the x is going from 3 to 4. The function's decreasing. And then we have our last one here. It looks so colorful. It may just be so confusing to you. I don't know. So it starts to move upwards again there after 4. So increasing from 4 to infinity. So for those of you that don't like using different colors, here's another option. if you mark these turning points here where it starts to change direction, you can take a look at sort of the slope. Over here, the slope is negative. In between 1 and 3, the slope is positive. In between 3 and 4, it's going down, so it's negative. After 4, the slope is positive because it's going up. So you can do it that way as well if you're using the same color, pencil for everything. Check the instructions on your homework. They may ask you to just put the intervals with a comma in between. Sometimes they don't know how to code the U, or it doesn't have the U symbol as an option. Okay, so just double check with your homework on when you're inputting it in MOM. Local absolute maxima and local absolute minima. So we've got local maxima, and maxima is just the plural. Maximum is the singular. So local maxima occurs at the highest point over an interval. Okay. Here's a little tip from your Aunt Lainey. When it says interval, by definition, that means there must be points to the left and right. In other words, an end point of a function can't be a local max or min. Okay, it can be a global or an extreme, but it can't be a local. Must be points left and right, must have points left and right, sorry. It's just bad grammar, that's. Now, an absolute maximum, okay, because if it's absolute maximum, it's the tallest. There's only one of them. Sometimes it's called the global maximum. And it is the highest point of the entire graph. So that's why we're using the singular, maximum. And this one can be an endpoint. Local minima, again, that's plural, occurs at the lowest point over an interval. And the absolute minimum, again, sometimes called global, is the lowest point over the entire graph. When you're talking about local max and local min, which variable goes up and down? The y, right? So usually local max and local min, we're looking at the y values, which would normally be like, your profit, your blood pressure, your population. So we usually state it as your local max is this, your y value, at x equals whatever. So there's an example. A local maximum is 9 at x equals 2. In other words, that's the point to 9. But 9 is really the maximum. That's how high the graph goes, or how high your function goes. So they want us to look back at the graph in figure 6. So there's that guy right there. And they want us to approximate any local maxima, any local minima for the graph, and then see if there's any absolute max or absolute. So we have a local local min, minimum. So a local minimum of -1 at x equals, what's the x value at that point? Okay. We have a local minimum of -1 at x equals 1, and maybe we'll do approximately 0.7 at x equals 4. So we had 2 local minimum. What about local max? So we have a local maximum of 1 at x equals, what x equals 3, okay? So we have those two. Now, do we have any global or absolute or extreme maximums? There's not one, and you're right, because we can't account infinity. It's not an actual point. Is there a lowest point on here?
We did have an absolute min to occur at x equals 1. It was the lowest point, which was -1 for the y. So we have an absolute minimum of -1 at x equals 1.
It's bigger. Okay. So this -1 here happens to be the lowest point over the entire graph, but it's also the lowest point among the points around it. So that is the lowest point within an interval of points. At x equals 3, it's not the highest point of the graph because we're going up towards infinity, but is definitely the highest point among the points around it. So within an interval. So same thing here at 4. It's a local min because it's the lowest points of the points around it, but not the lowest of the entire graph. So that's what we mean by locals. They're like little local vertexes almost, if you will. But because of the definition of local, if this graph, let's say it stopped here, this could not be a local point because I have points to the left of it, but I don't have points to the right of it. It has to be within an interval of points. It could be an absolute max or an absolute min of the entire graph. We just can't call it a local. You might see the word global, absolute, or you may see the word extreme or extrema. All of these are saying find the highest or lowest. Of the entire graph.